This lesson is part one of periodic trends, and we're going to focus on atomic radius. So I'd like to take a quantitative approach as well as showing you visually how this works and using electron configurations. So atomic radius is the distance from the center of the nucleus to the outside shell of electrons. So basically it's talking about how large an atom is. So we started in class by taking a look at this graph, and this graph demonstrates the atomic radius in picometers, which is a very, very tiny unit because atoms are very tiny, and graphing them against atomic number. So what we did was we determined where the periods would be. So the end of each period would be element 2, element 10, element 18. So we're looking at the noble gases, which are group 18. Okay, so here's helium, neon, argon, krypton, xenon, etc. So if that's the end of each period, that would mean that this right here would be period 2, this right here would be period 3, period 4, and so on. And what we can see is that as we go across a period, so we're increasing atomic numbers across period 2, across period 3, you can see that the atomic radius is decreasing. Now, as we go down a group, so for example, we said that these are the noble gases down here, so group 18, you can see that if we drew a line here, in general, you can see that the atomic radius is increasing. So it's pretty intuitive that as you go down a group, that atomic radius would get larger. But I think most people are surprised to hear that as you go across a period, the atomic radius gets smaller. So forgive me here, I do not have one of those fancy pens for writing on a touch screen, so I'm just going to have to use my finger. It might be a little bit sloppier than I'd like. If we were to use electron configurations to demonstrate how atomic radius increases going down a group, could use group 1. So hydrogen would have an electron configuration of 1s1. So we would only be to the first energy level or the first shell of electrons. Then lithium would have an electron configuration of 1s2, 2s1. So we went to the second energy level. Then sodium would have an electron configuration of 1s2, 2s2, 2p6, 3s1. Okay, now we're filling the third energy level. Okay, so that's going to be a larger atom than hydrogen. Now, as we go across a group, across a period, we are going to be adding electrons to the same energy level as we go across that period. So lithium, be 1s2, 2s1. Then beryllium would have an electron configuration of 1s2, 2s2. So we've added a second electron to the second energy level. Then we go to boron, which would have an electron configuration of 1s2, 2s2, 2p1. Now we've added a third electron to still the second energy level. Okay, carbon, B1s2, 2s2. Oops. That 2 got a little crazy. 2p2. Okay, now we have 4 electrons in still the second energy level. Okay, so the second energy level is going to be approximately the same distance from the nucleus. So we're adding more electrons to the same distance from the nucleus, essentially. Okay, this might be a little bit of an oversimplification, but let me erase this so we can go to the next slide. Okay, so meanwhile, as we're adding more electrons to the same energy level, the nucleus is becoming more and more positive because you're adding more protons. And that more positive nucleus is going to have the ability to pull those electron shells in tighter because they are the same distance. Okay, so atomic radius increases as you go down a group because you're adding more electron shells or adding more energy levels. And atomic radius decreases across a period because you're adding more protons, increasing the effective nuclear charge, and the electrons are being added to the same energy level. This is going to cause the nucleus to pull that electron shell in tighter. Okay, so as I demonstrated, even though you're going across the period and adding more electrons, across a period, you're adding electrons to the same energy level. So they're essentially approximately the same distance from the nucleus. So I tried to create a visual here, so hopefully you guys can see how this works. So here's lithium. Okay, if we are in the second period, we're adding to the second energy level. So I used the planetary model just so that it'd be a little bit easier for you to visualize this. However, this is not what electron orbitals look like. This is just a representation. So lithium, we're just going to do elemental lithium, which would have 3 electrons and 3 protons. Okay, now watch what happens if we move across the periodic table. So we add another proton. Okay, so now we are dealing with beryllium. Beryllium has 4 protons. Here we got 4 electrons. We've added an additional electron to the same energy level. So what's going to happen is that nucleus is becoming more positive. It's going to pull that electron shell in tighter. So you can see that it got a little bit smaller. Okay, let me go back. Okay, so we added an additional proton, and an additional electron. That's going to cause the effective nuclear charge to pull that electron shell in tighter. So hopefully you could tell that got a little bit smaller. Okay, as we continue to move across the periodic table, okay, here we have 5 protons. So we are dealing with boron. We've added an additional electron still to that second energy level. Okay, so what's going to happen, that should say 5 plus, is that nucleus is going to pull the electron shell in tighter. So we keep getting smaller. Here, if we've got 8 protons, 8 electrons, this is oxygen. Okay, again, pulling the shell in tighter. Okay, so if you're thinking about it in terms of a magnet, the closer the magnet is to something, the stronger the pull, and the larger the magnet, the stronger the pull. So think about the nucleus as we're adding more protons is basically creating a larger magnet that's going to pull that shell in tighter. So let's back up. Okay, so the more positive the nucleus gets, the tighter the electron shell is going to get pulled in. So let's do some practice problems. So you have these elements on your notes. So we are going to locate them and determine which one is the largest and which one is the smallest. All right, so let's go ahead and locate these. We have potassium, aluminum, phosphorus, and chlorine. So we know that atomic radius is going to increase apologize, I don't have that fancy pen yet. Let's do it this way. Increase going down, and it's going to decrease going across. So the smallest element is going to be the one with the least number of electron shells, so the furthest up on the periodic table, and it's going to be furthest to the right. So chlorine only fills 3 energy levels. And as we've gone across from aluminum to phosphorus to chlorine, we are adding more protons, which is pulling that electron shell in tighter. Okay, so they were all being added to the 3rd energy level, which is approximately the same distance from the nucleus, allowing that electron shell to get pulled in tighter. Potassium would be the largest, and that's because it has the most energy levels, or the highest number of electron shells. All right, next example. So basically, if there's a hierarchy here for deciding which one is the largest and smallest, how far down a group matters the most for determining how large it is. Then you would break that tie by looking at how far across. All right, let's try another one. So arsenic, just right here, sulfur, fluorine, and helium. Okay, again, the most important thing is determining which element is the furthest down, because it would have more electron shells. So helium would be the smallest, and arsenic would be the largest because we've gone down to the 4th period. We're filling the 4th energy level, whereas helium was only filling the 1st energy level. That one was pretty easy. Now we have radon, magnesium, beryllium, and calcium. So these elements are all in the same group, so we won't have any tiebreakers here. The smallest element will be beryllium. This has the least number of energy levels or electron shells. And the largest will be radon because it has the most number of electron shells, or the highest energy level. All right, now we have fluorine, boron, oxygen, and nitrogen. So which element is the largest, smallest? Well, we know that as we go across a period, we are adding more electrons to the same energy level, and the nucleus is becoming more positive, so it's pulling those electron shells in tighter. So it's decreasing as we go across. That means that boron would be the largest, and fluorine would be the smallest. Okay, that effective nuclear charge is going to pull that electron shell in tighter. Okay, think about it as a larger magnet in the middle. It's going to have a stronger pull on those negatively charged electrons. Okay, so now we have lithium, aluminum, antimony, and astatine. Okay, So all these elements are in different periods. Okay, so we're filling different energy levels. So this one should be really easy. Astatine would be the largest because it's the furthest down. It has the most electron shells or the most energy levels filled. And lithium has the least number of energy levels or the least number of electron shells, so it would be the smallest. Let's try a little bit more challenging one. So this one is not in your notes, but you can go ahead and add it in. The nice thing about printing out the PowerPoints is that you have space to write in extra notes. So let's see. Let's do lithium, fluorine, aluminum, and chlorine. And now what we're going to do is we're going to write these in order of largest to smallest. So first of all, our largest element is going to be the one that's the furthest down. Okay, so aluminum and chlorine here are in the same period. They have the same number of energy levels. So now we have to break the tie between aluminum and chlorine. So we know that atomic radius is decreasing across a period. So that means that chlorine would be smaller than aluminum. We would have a higher effective nuclear charge on chlorine. So it would pull that third energy level or third electron shell in tighter. So chlorine is smaller than aluminum. So if we're writing them in order from largest to smallest, make sure you make note of that. It'd go aluminum, then chlorine. Okay, and then we would need to decide which one is the smaller and the larger one between lithium and fluorine. So lithium is further to the left. So as we go across here, we're increasing the effective nuclear charge, which means the electron shells would be pulled in tighter. So fluorine would be the smallest. Notice I keep repeating the reasons why each of these elements is the largest or smallest, and that is because you will be responsible for that. I will give you these arrows like I have at the top saying increase or decrease for each trend, but it's important that you can describe why each one will be the largest or smallest. It will not be an acceptable answer to say chlorine is smaller than aluminum because it's furthest to the right, or chlorine is larger than lithium because it's further down. You do need to be able to describe in terms of electron shells, whether that be energy levels increasing or the effective nuclear charge increasing, which would pull the electron shells in tighter.